workstation. Now let me see if I can make this a bit bigger. There we go. So what I do want to introduce is the Spider IDE, or Integrated Development Environment. And I think we talked about this a little bit last week, but this is how I really like to be able to run my code, my Python code. The reason that I like it, I think, as opposed to, a lot of people like to use Jupyter notebooks, I sort of prefer an environment like this because it provides me with a couple of things. Number one, I have an editor over here on my left, and this is where I'm writing all of my code. Number two, and this is the most important thing for me, is I have this variable explorer up here. And I'll show you the advantages of that after we run a little bit of code, but it's a really nice way to be able to see what's really happening with your data as you're moving through the process. You'll likely have many steps where you need to actually see the data sets to be able to debug an issue, and it's really helpful to have those there. And then down in this lower right corner is what's called the console. The console is representative of a command window. So if you were to open up a command window, you can do that, by the way, by just typing CMD into Cortana. Let me show you that.
Usually if you started with MATLAB, you prefer Spider.
So that's one of the reasons that I like it. The comment was, and remember, I'm the only one mic, so I have to repeat it for you. The comment was that usually if you like MATLAB, or if you started in MATLAB, you like Spider. That would be the same for R also. R is set up in or some of the IDEs for R are set up in a similar kind of way. So anyway, this is what a command window looks like, and so the console is set to have a similar output. Anytime I have a print statement in my code, it will display to the console, or I can work directly in the console without running code. So, for example, without running this code over here, I could, if I just wanted to make some X data, oh, never mind. I actually have to bring in all these packages first. Okay, let's try that again. There we go. And now we'll make the data. So let's look at this variable explorer actually really quickly. So the nice thing here, so it shows me the name of my data set, the type of the data. So in this case, these are floating point or double precision, likely double precision numbers. And remember from last week, a floating point number, we're going to just consider to be a decimal number. Now I can see the size or shape of my data set, so I know that there are 100,000 rows in just a single column. And if I actually want to visualize my data, I can double click on it here, and I can see the X data that was actually generated, which is kind of neat. So, and let me go over just actually a couple more things about Spider before I forget. So in Python, comment characters are these hash characters here. And you'll notice that here I have a hash character followed by 2 % signs, and that's how I do what we call block programming. So you'll notice that I have my cursor focused, or I've clicked inside this block here, and it's now highlighted as a different color. The preceding block is a darker color, and you'll see the block after is also a darker color. So this highlighted block is going to be my active block of text. So the advantage of block programming is that you can run only select parts of your code if you want, instead of running the entire code. Sometimes running your entire code can be very time consuming depending on the types of operations that you're working on, so block programming can be very advantageous. So if I want to, this is my first block, if I want to run just this block and I want to advance to the next block, I'm going to press Shift-Enter. And I've done what's called run and advance. I have ran the block that I was initially focused on, and now I've advanced to the next block. So you'll notice that my focus is now on this next block, and by focus I mean that this block is highlighted or active. So again, I can press Shift-Enter and run and advance to the next block. If I only want to run this current block, but I don't want to advance to the next block, it's Control-Enter. So instead of pressing Shift-Enter, I just pressed Control-Enter. So now what we've done here is I've created all of the data. This is or it should be the exact same code or very, very similar to what we saw during the PowerPoint presentation. So here I have just created the data, right? What I've done is I have created 100,000 random and normally distributed numbers, and I've squared those numbers to create my Y data. And then in the second part of the block, I've partitioned the data into that 90-10 split. In this block, we're just building the DLM. The deep learning model. I do have, I think maybe a little bit of extra code in here. For example, I'm using a timer. I often just put timers on codes that I run. And when I say a timer, what I'm doing is I'm creating a starting point when I begin running the code, and then I time how long it takes the code to run. I think I do that maybe because I'm just a touch anal retentive and I'm not particularly patient waiting for codes to run, so it helps me to know how long to expect it to run, I guess. But that's just something that I personally find helpful, so don't worry too much about that. And same thing, so I'm bringing in I create the main input here. I create the hidden layer. In this case, actually, it looks like I put in a second hidden layer. So now we have 2 hidden layers, and that's great. And I have my output layer here. I'm going to create the overall model and let Keras know which inputs and outputs to expect, or which sort of shells to expect that I created up in the lines above. I'm going to compile the model with a couple of options. So here what I'm doing is I'm specifying the loss function that I want to use, or the way that I want to calculate the residuals between my true data y and my predictions y hat. I'm specifying the optimizer. In this case, Adagrad is what you would call a second order optimizer. It's probably overkill for this situation, but it certainly doesn't hurt. Elizabeth, do you have a question?
Yes,
Yeah, what's going on?
about where you're creating the hidden layers, where it says like add dropout to hidden layer.
Oh, yeah.
What is that?
Okay, so the question was, let me scroll up a little bit so you can see that. The question was, when creating the hidden layers, what does it mean to add dropout to a hidden layer? So we'll talk about this a little bit more in the coming sessions, but dropout is a regularization technique. And remember, a regularization technique, or just the process of regularization, is something that we do to avoid the model overfitting or creating a mapping based on memorization as opposed to true learning. And so really what's happening with dropout is that we're saying on every epoch, ignore a random certain number of samples. So I think I set the dropout rate to be 20% or something like that, right? So what that means is that every time I'm going through a training epoch, I'm instructing the computer to forget or just ignore a random 20% of my data to help avoid the memorization problem or the overfitting by looking at all samples for every epoch. Does
that help with a nonlinear distribution of your sample points?
Does that help with a nonlinear distribution? No, it has nothing to do with that. So it's not that whether the function I'm trying to predict is nonlinear or not isn't necessarily a problem when it comes to overfitting. If I have, in this case, I had very few parameters in my function, but so I have a relatively low dimensional space, right? But in a high dimensional problem, the issue is that you have, basically an ill-posed problem where you have more parameters than you can really, appropriately sort of determine. And so that does become an issue, yeah. So let's look at how this, the rest of this code is set up, and I just want to make sure that I didn't put in anything crazy. I think these are a couple things here that I didn't talk about, so let me talk about that now in the presentation. So Keras has a number of what are called callbacks. And in this case, I'm using 3 different callbacks. I'm using something called CSV logger, early stopping, and reduce LR on plateau. And let me talk about what each of those are. So a callback function in Keras is a function that's going to be running alongside our neural network that's usually collecting and storing some kind of metric, or is usually used to do a little bit of model training control. So CSV logger basically just creates a CSV file of all of my metrics over time of every epoch, right? So it's actually all of the same information that is stored in the history object that we talked about earlier. But in this case, I have a record of that once I close this IDE, right? So I can create that history object during my model run, but of course, once I close down my program, all the variables I've stored don't exist unless I wrote them to a file. So this is a way of writing that information to a file so that later, if you wanted to reload that model and maybe you want to plot up some results or something from your previous model run, that's just a nice thing to have, and it's a really lightweight, it's just a CSV, right? It's a very lightweight file, not going to take up much room. So that's a callback that I personally like to use. The next callback is called early stopping, and what this is going to do is it's going to monitor our runs, and if in between two different runs or in between a number of different runs, I have no improvement in my overall prediction or in the minimization of that residual, then it's just going to stop early. So I could say, I think I set this model to run for 5,000 epochs, right? And as a modeler, that's just my guess of how long I think that the model is actually going to take to train. But what if I actually perform a really good optimization within 2,000 epochs? Then I have to continue running for another 3,000 epochs, and that could be overkill. I could cause some overfitting errors in doing that. And additionally, you'll see, or I don't know if you guys tried running this model, it runs very, very quickly because there are very few parameters that need to be identified for the mapping. But, normally you'll have, I've had some models where every epoch takes 3 to 5 minutes to run. So if I were able to save myself 3,000 of those 3 to 5 minute intervals, that saves me as a researcher a lot of time. And so employing early stopping can be a good thing to do. I will caution you against that though, because sometimes you can stop too soon, right? You can stop, what you don't want to do is you don't want to stop the training of your model before your loss function has converged. So that's something that's really important to monitor, and that might take a little bit of trial and error. What I mean by converge, we assume that this function has converged at or close to 0 when we see it really plateau out. The reduce LR on plateau, LR means learning rate. So remember we talked about that learning rate parameter and how that sort of sets the step size during the minimization process. So what will happen over time is that as the model gets closer and closer to convergence or to reducing that residual to 0, what will happen is that the changes that you need to make to your weights and biases become vanishingly small. And so if the learning rate is too large, you'll actually ping pong around the global minimum as opposed to actually reaching the global minimum. And so when you see that ping ponging, what we really think about is that we think about the loss function having plateaued because we're not seeing any improvement, right? And so when we see that plateau, what I'm telling Karis is I want you to reduce the learning rate, make that step size a little bit smaller, and let's try again to see if we can reach that global minimum. And this is something that just in my own experimentation using neural networks and using Keras, I've had a lot of success reducing the learning rate. In fact, if you're plotting up your loss and it looks almost like a sinusoidal function, right? Where you see some kind of harmonic, almost like vibration, that's the ping-ponging of your learning rate going back and forth, and it probably means that you needed to employ this callback a little bit sooner in the process. So that's just kind of an interesting aspect of Keras that I don't think I pointed out on the PowerPoint slides. And then this block you've seen before, which is where the actual training is happening, and we're doing some testing and predicting down here. So let me go ahead and run this block. And again, I'm just doing Shift-Enter to run that block. Now, again, the number of parameters that we're trying to identify here in order to create that mapping from X to Y, the number of parameters are very small. So you'll see in this summary, we had 4,353 parameters to identify, which sounds like a lot, but in a typical neural network, you'll have hundreds of thousands or millions of parameters that you're trying to identify. So 4,000 is really nothing. And we just ran 5,000 epochs in less than the amount of time that it takes sometimes to do a single epoch on a larger data set. So that, again, is slightly atypical behavior, and that's just because we're doing a very simple demo. But let me show you a couple things about the output here. So the way that this looks on the screen, this is nothing that I've programmed. This is underlying code in the framework. But it's, the nice thing here, so I get an output from every epoch, and what I get is my overall loss on my training set. I think in this case I asked it to calculate a metric of mean absolute error at every epoch. And then also I can see what those same values are, so the loss and the metric on my validation set. So when it says just loss or mean absolute error, those are metrics that are calculated on the training data, and then I can see also at every epoch how my model is performing on my validation data as well. So I can track that over time. With the callbacks actually that I showed you earlier, let me scroll up again. Yeah, there we go. So in this case, for the early stopping and the learning rate reduction, I need to monitor a particular quantity to be able to, so I'm monitoring either my loss usually or my validation loss. Personally, I'm interested in monitoring the validation loss because I really want to know when that has been minimized. It almost doesn't matter to me if my test or if my training loss is increasing a little bit. What I really want to do is I want to reduce the validation loss. And so that tends to be the quantity that I monitor, although I'm willing to be wrong about that. It's very possible that that was the wrong choice. But in this case, and for me personally, it's worked out quite well. And then I think at the very, oh, whoops, I'm scrolling the wrong way. I think at the very end here, I put in, I think I just print out a summary. And so this is a nice way of just looking at your network and sort of understanding how the shapes are working as you move from layer to layer, right? So in this case, remember I used a batch size. So I used a batch size of 5,000. What the batch size means is that during every epoch, I'm actually only going to process my data in small batches of 5,000 instead of using, I think, the 90,000 altogether. And the reason that I do that is that, again, it's a form of regularization, and we can talk more about that later as well. So my shapes here are going to be listed in terms of my batch size, not in terms of my original input. And I'm saying batch size for the X coordinate or the number of training samples or testing samples, whatever you want to say. And then, of course, the number of features. So you'll notice, remember in these hidden layers, I passed in a hyperparameter for the number of nodes. So I put that number of nodes into each of these hidden layers, and then I've then compressed that shape again to make my output data. So it's an interesting sort of way to think about the latent space. And then, of course, the number of parameters associated with each of these layers. You'll notice, interestingly enough, that the number of parameters greatly increases in between my two hidden layers, right? In my first hidden layer, I'm looking at 128 parameters. By the time I get to my second layer, because I'm carrying, of course, parameters through, I have 4,160 parameters. So you can see that the deeper our network becomes, in addition to the parameterization of the problem itself, can exponentially increase the number of parameters that you're working with. So one of the things that we look at when we're really looking on optimizing the performance of a network is how many hidden layers do we really need to be able to accurately predict or to be able to describe the latent space of this problem, right? And now let's look at a couple plots. There we go. Okay. So let me actually, I think I have a PDF of this guy up. Yeah, this is interesting. So remember, this is the function that we are trying to plot here, this y true. And I've gone ahead and I've overlaid our actual y hat predictions on top of that. Now what you'll notice is that through the portion of the data where we have near continuous data, we're essentially predicting the exact same number, right? You can see these two functions are really sitting on top of each other. However, as we approach the tails of our data set, where we have what we consider extreme values or outliers, not only do we have fewer data points, but we also have some data points like these endpoints, which have no data on the other side of them, right? Or at the other extreme. And so it's very difficult to predict that data point in particular. So you'll notice that the closer that we get to those tails or to those areas of more sparse data or extreme data, that our predictions tend to perform poorer at those points, which is just interesting. So I think at this point, if you guys have, sorry? Yeah,
you try with less data number in the bottom part, the value part of your.
I'm sorry, can you say that again?
Have you tried with lesser data number in your value part of this function?
You mean have I tried like doing different distributions of the data set and maybe putting a larger concentration of data over here as opposed, you know, I didn't really do much experimentation there. I certainly could have. I think what you're asking is, you know, if we had sparse data through maybe this portion of the function as opposed to the tails, what would the predictions look like? And that's an interesting experiment. Maybe we should try doing that just to see what works, you know. You know, I know that this is an extraordinarily simple example, right? Y equals x squared. Never would you need to create a neural network to predict y equals x squared in a functional sense, right?
Yeah. So
the reason that I like to work with really, really simple examples like this is so that you can experiment with things like that, right? So that you know, obviously we have a known expectation of the behavior of this function for any data point that we put into it. And so, you know, if we make changes in the neural network, it's easier to view the effects, I think, when you use really simple
especially
functions.
also about the hyperparameters.
For the hyperparameters too, yeah. So, you know, I didn't talk too much about that today, but all of those hyperparameters that I set, and there are more, you know, obviously that we could set for a more complicated network, but all of those hyperparameters, I just set essentially arbitrary values for, right? So the number of nodes, the number of epochs, the batch size, you know, those are parameters that you really want to optimize. So what I will say is that, you know, there are sort of two larger steps in this overall process that when we're talking about working with the data. One of them is pre-processing, which in this case I didn't really focus on, but I probably should have. During pre-processing, we generally normalize the data. And the reason that you do that is in a real world sort of sense, you know, often you'll have parameters that are measured on different scales or with different units, right? So you might have, you know, values that are much greater in absolute value than others for other features, and so you normalize the data. And then, so there's your pre-processing step, and then of course your hyperparameter optimization. So generally, what I have found and what I find to be sort of a trend in the deep learning community is that I would say 90% of your performance enhancement when it comes to the overall prediction of your network, probably 90% of that success is going to occur during the pre-processing phase in how you treat your data. And minor speed-ups, I think, can be done with hyperparameter optimization. But when we're talking about minor speed-ups in terms of, you know, training, you know, 100 million samples over, you know, 5,000 or 10,000 epochs, even saving a couple hours or a couple days of training time, that could be considered a minor speed up, but for us it's a really big deal, right? So I definitely don't want to imply that hyperparameter optimization is not worth putting your attention to, but I think that, you know, I've tried to twist those knobs before I really figured out the pre-processing step, and what you end up doing is just digging yourself into a hole where really all you're doing is predicting artifacts, right? Because you have errors in your data, or the pre-processing wasn't done appropriately. So that's an interesting sort of
step to take, yeah, right.
So if you had like data that all came, let's say from like the same machine, would you need to normalize that?
So the question was, if you had data that all came from the same machine, would you need to normalize that? So I think what you're saying is if you have data that, like let's say the only data that I'm feeding in are, that have the same units and were measured from the same machine, would I still need to normalize that? And that's a really good question. And the answer to that is yes, you do need to normalize that. So the reason that you want to do this normalization process is, remember what we're really doing is we are trying to calculate the gradient of a function. And so if we use very, very large numbers, those that sort of vary on different scales, those gradients actually get a little bit more time consuming to compute because we actually have to store larger numbers in memory. And whenever you store large numbers in memory, you use up a lot of memory very quickly. And remember, we're already using a ton of memory just to be able to pass these very large training data sets through and to be able to store the graph or the structure of this network. And so one of the reasons that I would say probably, I mean, in my opinion, I'm willing to be wrong. You know, now that I have videos of this, I'm probably, you know, documenting many ways that I'm wrong, right? But, you know, one of the really important things is to be able to create, I guess, the best potential for your network to do very well. And that's another reason for using those activation functions. So a lot of times people talk about the activation function as squashing your values within a particular range. And that, again, makes that gradient optimization a little bit more manageable, especially in terms of your memory usage. I don't know if anybody else had, Devajit, you're not, oh sorry, Devajit, you're nodding, you might be actually more knowledgeable about this stuff than I am.
So it's about memory usage.
Yeah.
When you are loading the data, it might be a problem. Like if you have a very large amount of data set, it will take much memory, and for further processing, you need more resources than loading of your data like that.
Yeah, so I think, and I'm just going to repeat what you said.
Yeah.
So I think that the suggestion is to have your data normalized before you load it in, before you're actually running the network. Yeah, so that's a really good idea. So I generally, and I'll show you guys maybe that would be a good thing to go through, it'd be a workflow the next time that we actually get together in creating these networks. So I'll amend what I was going to do next time, but yeah, so I think maybe that's a good thing to focus on, that there should be a separate pre-processing step. You know, in this case, this is a relatively small network, it's a relatively small amount of memory, and so I sort of condensed that pre-processing step in with the actual model training, but I think you're right that it's really important to sort of separate those as two discrete tasks, right? And we'll talk a little bit about different ways to store files in different file formats and things like that that work better with Kira than some others, right?
If I can add one thing?
Yeah, absolutely.
So, especially with geoscience data, like even if you have one system that's acquiring all your data and it's consistent, right? One data acquisition system connected to one sensor, like typically what happens is our signals vary in both time and space. Right? So even if it's the exact same system acquiring the exact same signal, that's going to change over time because
So,
the Earth.
yes, so
right?
the comment is that, you know, regardless of, and correct me if I'm wrong, but the comment is that regardless of whether or not you're using the same machine or you know, instrument to measure something over time, that there is going to be variation in the accuracy of those predictions. So that's a little bit different than what we're talking about with scale when we're talking about pre-processing the data. Yes, we understand that there is both measurement noise and probably some, you know, measurement error in there somewhere, you know, that generally just happens when you're taking measurements, right? There's some noise and variability over time. We take that as a given in the input data, and actually it's a really good thing to have that noise in your input data, because what it does is it helps to, I'm trying to say this in a way that doesn't make it sound too flowery, you know what I mean, but I think that it sort of creates it shows the computer many, many examples of the variability that we expect to occur, or that would occur under normal circumstances. And so having somewhat noisy data, while normally in more of a physics-based approach would be a detriment, I think in a data-driven approach is actually a really wonderful thing, because what we really want is a large volume of data that represents the true system state, which includes that variability in noise. So that's actually a wonderful thing to have. Did you guys have any more questions at the moment? Okay, let me see how we're doing on time. Okay, so we still have some time. Do you guys want to look at an application? Yeah, okay, you're nodding, okay. Cool, so let me make sure I'm focused on the right screen here. There we go, okay. So I'm going to talk a little bit about how I've applied neural networks in my own research, and we'll talk a little bit about the difference between physics-based and data-driven models. I think I've used those terms a couple times so far today, and I don't think I've really dedicated myself to explaining them. So let's talk a little bit about that now. So the application that I'm going to talk about is with my own research, and what I'm really trying to do is I'm trying to predict soil moisture, or really I'm trying to predict surface water flux. And I'm doing that using a model that was created by the USDA called the Soil and Water Assessment Tool. And this is just a little cartoon actually from some of the SWOT documentation, Soil, Water, and Assessment Tool. We usually say a SWOT. So this is just a picture from this documentation for this model. And what I really just want to point out are the individual flux components here. So what we're trying to do is we're trying to predict soil moisture, so the amount of water that remains in this near surface yet subsurface environment. And we're doing that using these different flux components as precipitation, evapotranspiration, surface runoff, and percolation into the shallow aquifer. So precipitation is going to be the input or total amount of water. Surface runoff is going to be the amount of water that is precipitated onto the surface, onto the ground surface, but doesn't actually infiltrate into the near surface environment. It just runs off of the surface directly into stream channels. Evapotranspiration is the amount of water that either evaporates from the ground surface or is used by plants, which would be transpiration, And percolation to a deeper aquifer would be water moving down the soil column into the deep aquifer and away from the near surface environment, or shallow or deep aquifer, either way. So actually what we can consider here is that this equation for soil moisture we can almost consider as an analytic equation or a physics-based equation to be able to estimate soil moisture. So what I mean by that is that what we've done here is we've made some assumptions, some simplifying assumptions as scientists. And what we've said is that we can approximate the amount of soil moisture we have if we know these other variables, right? If we are aware of the other components of flux and are able to quantify those, then we should be able to predict soil moisture using sort of a plug and chug method in this analytical equation.